The Foundations of Geometry by David Hilbert. Chapter 5, Desargues' Theorem. Section 27, Equation of the Straight Line based upon the new Algebra of Segments.
In sections 24 through 26, we have introduced into the plane geometry an algebra of segments in which the commutative law of addition and that of multiplication, as well as the two distributive laws, holds. This was also done upon the assumption that the axioms cited in section 24, as also the theorem of Desargues, were valid. In this section, we shall show how an analytical representation of the point and straight line in the plane is possible upon the basis of this algebra of segments. Definition: take the two given fixed straight lines lying in the plane and intersecting in O as the axis of x and y respectively. Let us suppose any point P of the plane determined by the two segments x, y, which we obtained upon the x-axis and y-axis respectively, by drawing through P parallels to these axes. These segments are called the coordinates of the point P. Upon the basis of this new algebra of segments, and by the aid of Desargues' theorem, we shall deduce the following proposition. Theorem 34. The coordinates xy of a point on an arbitrary straight line always satisfy an equation in these segments of the form ax plus by plus c equals 0. In this equation, the segments a and b stand necessarily to the left of the coordinates x and y, and the segments a and b are never both 0, and c is an arbitrary segment. Conversely, every equation in these segments and of this form represent always a straight line in the plane geometry under consideration. Proof: suppose that the straight line L passes through the origin O. Furthermore, let C be a definite point upon L, different from O, and P any arbitrary point of L. Let OA and OB be the coordinates of C, and xy be the coordinates of P. We shall denote the straight line joining the extremities of the segments xy by G. Finally, through the extremity of segment 1, laid off on the x-axis, draw a straight line H parallel to AB. This parallel cuts off upon the y-axis the segment E. From the second part of Desargues' theorem, it follows that the straight line G is also always parallel to AB. Since G is always parallel to H, it follows that the coordinates xy of the point P must satisfy the equation Ex equals G. Moreover, in figure 49, let L' be any arbitrary straight line in our plane. This straight line will cut off on the x-axis the segment C equals OO'. Now, in the same figure, draw through O the straight line L parallel to L'. Let P' be any arbitrary point on the line L'. The straight line through P' parallel to the x-axis intersects the straight line L in P and cuts off upon the y-axis the segment Y equals OB. Finally, through P and P', let parallels to the y-axis cut off on the x-axis the segments x equals OA and x' equals OA'. We shall undertake to show that the equation x' equals x plus c is fulfilled by the segments in question. For this purpose, draw O'C parallel to the unit line, and likewise CD parallel to the x-axis, and AD parallel to the y-axis. Then, to prove our proposition amounts to showing that we must have necessarily A'D parallel to O'C. Let D' be the point of intersection of the straight lines CD and A'P', and draw O'C' parallel to the y-axis. Since in the triangles OCP and O'C', the straight lines joining the homologous vertices are parallel, it follows, by virtue of the second part of Desargues' theorem, that we must have CP parallel to C'P'. In a similar way, a consideration of the triangles ACP and A prime C prime P prime shows that we must have AC parallel to A prime C prime. Since in the triangles ACD and C prime A prime O prime, the homologous sides are parallel to each other, it follows that the straight lines AC prime, CA prime, and DO prime intersect in a common point. A consideration of the triangles C prime A prime D and ACO prime then shows that A prime D and CO prime are parallel to each other. From the two equations already obtained, namely EX equals Y and X prime equals X plus C, follows at once the equation EX prime equals Y plus EC. If we denote finally by n the segment which added to segment 1 gives the segment 0, then from the last equation we may easily deduce the following. Ex prime plus ny plus nec equals 0. And this equation is of the form required by Theorem 34. We can now show that the second part of the theorem is equally true. For every linear equation ax plus by plus c equals 0, may evidently be brought into the required form ex plus ny plus nec equals 0 by a left-sided multiplication by a properly chosen segment. It must be expressly stated, however, that by our hypothesis, an equation of segments of the form xa plus yb plus c equals 0, where the segments ab stand to the right of the coordinates x and y, does not in general represent a straight line. In section 30, we shall make an important application of Theorem 34.
The Foundations of Geometry by David Hilbert. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898 and 1899. It was translated by E. J. Townsend, Ph.D., University of Illinois. The text was downloaded from Project Gutenberg with the following notice. This ebook is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. Read by Jim Renholt. Programming and illustrations by Jim Renholt. 2019. Portrait of David Hilbert by Rita Ray Renholt. Thank you for listening.